In this lecture, we're going to briefly discuss the RISC-V ISA. So the RISC-V ISA is not really required for studying this course, but then we might do some assignments which are based on some RISC-V course. So we can take this RISC-V core, which is available as the base processor, and we can build on top of this processor. The spec is very similar to the MIPS architecture we have seen earlier. So there you had a 32-bit ISA. So RISC-V also has a 32-bit ISA. So there are 32 registers called X0 to X31. X0 always contains the value 0. So these can be 64 or 32-bit wide. So if it's an RV32I base specification, they are 32-bit wide registers. The program counter is also 32-bit. It holds the instruction of the current, it holds the address of the current instruction. The RV32I has 47 instructions, and the data must be in registers to perform operations, so they cannot directly operate on memory. So they must be aligned on a 4-byte boundary in the memory. The memory is byte addressable, which means that each location in memory contains 1 byte of data. And to address the next word in the memory, word is 4 bytes, so you need to add 4. So for example, if PC is pointing to location 0, the next instruction is available only at PC plus 4, because each of this is 1 byte wide, and each instruction is 32 bits or 4 bytes wide. So this is how the byte addressable memory looks like, which you're already familiar with. You have 1 byte in each memory location, and you have to do plus 4 in order to get to the next instruction. So the RV32I or the RV64I base specification has these main instructions. These again are very similar in format to what we've seen in MIPS. So you have the loads and the stores. So for example, load word has this format: load word RD RS1 immediate. RD is the destination register, RS1 is the source register, and there is an immediate field. The way it works is similar to what we have seen in MIPS. So it is RS1 plus immediate. You go to that particular memory location and load that into the destination RD. So similarly, the store is also having the same format. Then there are arithmetic and logic instructions. So you have the add, sub, add I. I'll talk about this instruction later on, which is called load upper immediate. I'll talk about this later. Then you have very similar logical instructions as similar to MIPS. You have the XOR, XOR I, and I, or I. So wherever you have just the registers, you have 2 source registers and 1 destination. Wherever you have the immediate field, you have the immediate field, the source, and the destination. Then you have the shift instructions. So the shift left, and the shift left immediate. So if you have the shift left, the shift is the shift left logical. So you're going to shift left RS1 by an amount present in RS2 and store the result in RD. Then there are a set of compare instructions. So this is set on less than. Again, we had the similar instructions in MIPS. So if RS1 is less than RS2, you set the destination destination to a high value, otherwise you set it to the low value. So this is very similar to what you have in MIPS. Then you have the same branch instructions. You have BEQ, so you're going to compare you're going to have a compare operation here. So if RS1 is equal to RS2, you're going to jump to a certain location. I'll describe this in detail later. So we're going to use this immediate field and jump to a certain location, or in other words, we're going to branch to a certain location if RS1 is equal to RS2. And if it is not equal, then you use the PNE instruction. If RS1 is not equal to RS2, so then you're going to jump to a certain location. Then you have the jump instruction. So here they call it jump and link. So they call it JAL. So so here this is not going to check any condition. It is just going to jump to a certain location again specified by the immediate field. I'll describe this again later. But why do we have RD here? Because you also want to return back to the main program from where you're jumping. So you're going to have this as return. The return address basically is going to be stored in RD. So this is just an example, just to repeat from what we did in MIPS. So if you have an instruction such as this in high level language, how are you going to convert this into a RISC-V assembly code? Assume that this is a 64-bit ISA, and assume that H is associated with register X21, and the base address of this array is present in X22. So this is, I'll just show you the uh, solution, and you can work this out. So basically you have the source, the base address of the array in X22, and when you say A of 8, it's basically you have a memory where you're pointing the A, and then you go to 8 locations from this A, and this is a 64-bit ISA, and therefore you're going to multiply that by 8, and therefore you're going to jump to the eighth uh, double word and then fetch that content, and therefore this is 8 multiplied by 8, and the base address is X22, so you're going to basically add this to that base. That's why you have X22 here. So this is X22 plus 64. You're going to go to that memory location and then load that content into some temporary register. Let's call that X9 here. Then we're going to add that to H. H is associated with X21 as specified here, and then we're going to add the two and store the result, and then finally store this back into A12. So A12 again is the 12th double word, so 12 multiplied by 8, because we're talking of 64-bit IC. So that's how you have the store. So remember, now we are doing double words, so therefore it's not LW, but it is actually LD. And just in case you've forgotten, how we represent data is you have a hexadecimal number like this. Each of this is going to be expanded into binary. So don't put this into the calculator and then calculate the binary, but then you got to take each of this and then convert that to 4-bit binary. And that's how you get a 32-bit representation.